everyone, in today's video we're going to have a look at CAD and CAM for the exam content. So this is going to be on your paper 1, the 2.5 hour paper. So before we get into it, a couple of things that you basically need to make sure you know at the end of this for your exams. So what CAD and CAM are, how CAD and CAM can be used in industry, different kind of CAM machines that you'll use. So these three are more of the GCSE sort of subject knowledge I was expected to be at. The first two definitely. The third one hopefully a little bit you're aware of, like laser cutters and that sort of thing, and 3D printing. And then the bottom ones, computational fluid dynamics, also known as CFD, finite element analysis, rapid prototyping, electronic point of sale, and production planning and control networking. Those are very A-level specific, so I'm not expecting you to be like able to tell me about those now, but I'm hoping you've got a little bit of an idea of what the first two, maybe three are. Okay, so advantages and disadvantages. So first of all, as I said down here in big red, is don't refer to loss of jobs due to machines doing it instead. It's not like robots are taking over the world. This isn't the real life Terminator. They're not taking our jobs. What it's doing is producing different styles of jobs. So rather than having a skilled craftsman making a certain thing, there might be a new machine that can do that certain job, but you still need to have a person that can use that machine. So it's creating a different set of skills and a different sort of job that would exist that didn't used to exist. So advantages. So first of all, it speeds up the whole design and the whole process. So if you take like Fusion, for example, because we use Fusion 360 a lot in college, once you're sort of like doing a design, it's very easy to do, like make developments and make change. Once you've got your base model done, you can always go in and remodel. You can change materials really easily. You can make tweaks to it. You can add fillets to it. You can change dimensions of it. Particularly, it's like parametric modeling, which means you can like change dimensions and the whole thing will change with it quite easily. So before then, you would have to just redraw it over and over again. So if you're doing like 6 or 7 iterations, you're redrawing from scratch each time, which can be a massive pain. And it also makes it a lot easier to work with designers in different locations. So you no longer have to be working in the same studio, in the same building, on the same floor, at the same table as someone else. So it's very easy for you to share work with someone in a different part of the country or a different part of the world. Particularly with like cloud-based now. You've also really easy to set up with CAM equipment. So particularly again, we'll take like Fusion. It's so easy to take your Fusion model and then you can save that as an STL so that you can 3D print it, or you can export it as a DXF so you can laser cut it, or you can CNC route it. So really, really easy once you've got the right equipment, the right software to set up for different CAM equipment that you've got. Some of the disadvantages are they have a huge amount of setup costs. Software itself is quite expensive. Now, obviously, being in education, quite lucky, particularly with like Autodesk, but a lot of companies do give students free educational licenses, which is huge. If you take like Fusion or take like SolidWorks, which are two of the bigger ones, they are massively expensive once you go into industry. Obviously, you're not the one paying for it; it's the business that pays for it, but it's hugely expensive. You've also got the hardware, so you obviously need to have decent computers to run it, but then also having the actual like laser cutters. So our laser cutter, which is a decent sized laser cutter, it's an industry standard laser cutter, that cost about £8,000. All right. You can get smaller ones, much like you can get 3D printers now, so you can get like an Ender 3, which is like 180 quid. Obviously, that's like entry level sort of hobbyist sort of 3D printer, but then you get like automakers and bigger industrial 3D printers, which can be thousands. I think I was looking at like a metal 3D printer because I was just window shopping for fun, and I think that was like £15,000. So the costs can be huge. But also remember, you need to be able to train the staff as well. So actually, someone who knows what they're doing needs to be able to like train those people. So you got to pay for that training as well. Software has to be updated regularly, which can be quite expensive. Now that's a bit of a weird one because some of them, if you take like Fusion, which is subscription based, so it's no longer a lot of software nowadays. It isn't a case of just you buy it and you own it. It's like with Microsoft Office and stuff like that, is you pay subscription for the year and they sort of like update it regularly. So Fusion updates every month, so it gets like new features and gets rid of bugs and those sorts of things. Others don't do that. So you take like SolidWorks, Rhino, and those sort of ones. They don't do that as much. They tend to just bring out like mainly yearly updates, but not always yearly updates. Depends on what's sort of going on. The other problem is it's not easy to just do like a quick sketch. If you've got like an idea and inspiration's just struck and you don't know, oh, I've got to quickly, you can't suddenly get your laptop out. Okay, I've got to turn it on. Okay, where's my mouse? Okay, so you can't quickly get a sketch like a little piece of paper, pencil, done. Okay, so both sides of the fault. It also comes down to a personal preference as well. So We'll start with CAD first. Just so you just in case you don't know, just to clarify, CAD stands for Computer Aided Design. All right. So I've mentioned a few in the previous slide. There are loads of different kind of CAD packages that you can use. We use Fusion 360 in college because they do educational license, and it's brilliant because it's very easy to use, got a nice friendly UI. You can export for 3D printing, laser cutting, and so on. You've got other ones like SolidWorks is like the big one, so they're the big top company. You've got other ones like Rhino, even things like Google SketchUp. So those are what's known as CAD modeling. The good thing about Fusion and SolidWorks, I'm not so sure about Rhino because I've never really used it much, is they're parametric, which means that you can sort of like input measurements and it will sort of be able to affect and like change later down the design. So those are technical, what's called a CAD modeling. Excuse me. You then have what is typically more referred to like 3D software. So that's be like your Maya and your Blender. Now Maya is made by the same people that make Fusion, and Blender is open source, so anyone can download Blender for free. So they'll still let you produce 3D objects. So I have modeled, on this screen here, two of these models are made by me. So I made the drill on Fusion. I've made this microphone, which I'm actually currently using, in Maya. So they're both very, very different packages. And the one down here, the F1, the Mercedes launch car, that was actually made in Blender. So, and I thought that was really interesting because when they had the launch of the new car for the 2022 season, they actually said at the start of it is the model then rendered in Blender, which I thought was really, really fascinating. So they both let you produce 3D objects, but what I would say is if you're going to make something functional and create technical drawings and that sort of thing, you go down the CAD route. Whereas if you're just trying to make a 3D object to look nice and pretty and promote and that sort of thing, you'd probably go down more the 3D software. You then can take those. So obviously, we know for a fact in Fusion you can render. Okay, you've got the appearance menu, drag and drop your materials and so on. But what you can do if you're going to get like more into the promotional, like making things look really, really nice, is you then have some 3D software that are specific for rendering. Now, the two big ones for that, Keyshot is the first big one, and that's very much as such that all that software will do is rendering. So you don't do any modeling in it. So you do your model in Fusion, do it in Maya, do it in Blender, whatever you're doing, export it, put it in, and drag and drop materials onto it. The other one is Substance Painter, which is made by Adobe. And that is more, so I have done this one in Substance Painter here, the microphone one, and that lets you put things like imperfections and basically will make things look a lot more realistic, so it almost looks photorealistic. Again, almost like with the car as well. So that's CAD modeling. So what we're going to have a look now is the CAM process. So CAM stands for Computer Aided Manufacture. So I'm hoping a few of these you have come across before. So we'll take the laser cutter first. That is one I'm hoping everyone's heard of before. They're quite used a lot in schools nowadays. They're actually very, very common. So what happens is that a laser beam essentially is used to cut the material. So you have a compressed air. So we have a CO2 laser in college, which are the most common ones. It's water cooled. So at the back of the laser cutter, there's a laser tube that essentially sends a laser beam through. And what will happen is the laser beam essentially hits mirrors. So I'm trying to get my cursor up. There we go. So the laser beam, it hits mirrors. So on our laser cutter, I think we have 3 mirrors. So the laser beam comes into the actual main compartment of the laser cutter, hits one mirror, that reflects onto another mirror, that then reflects onto the piece. Okay, and then for it to go in there, it's like a focal lens, almost like a glasses lens that focuses it, and then it will cut it down. So what you will have for that, you need a 2D drawing, which you can create in things like 2D Design or Fusion, and you need something called a DXF file. So these are machines that are typically referred to as CNC, which stands for Computer Numerical Control. Because when you do that, the machine isn't actually seeing your drawing. It doesn't see it as a drawing. What it sees it as is loads of numbers, like noughts, like coordinates. And that's basically telling it where to move. So lasers will move in X and Y axes. So hopefully we know, because we're so good at Fusion and CAD at this point, you understand that you have things in the X, Y, and Z. So Z being up and down, X being left to right, and Y being forwards and back. No. Y being left to right, X being forwards and backwards, Z being up and down. That may vary depending on what you're doing. But that's not the style that it'll work in. You've then got routers, which can be both 2D and 3D, depending on how modern it is. Again, you'll still have your DXF file if you're doing 2D, or if it's 3D, you're doing STL. This actually routing existed before laser cutting, and before laser cutting existed, you would use routers instead. Because rather than doing it with a laser, it does it with a cutter. So it's like almost like milling machines. So you have CNC mills. So you'd have what looks like a drill bit, but it's actually like a cutter. And it will cut through material essentially how the laser cutter would, but then you've got to take into consideration the thickness of the cutter and that type of thing. And it also let you cut thicker material, so you can do timbers. Obviously, laser cutter, unless you've got a really powerful one, you typically do like 3 or 6 mil thick material. You might do 9 at a push, but you probably wouldn't. Whereas routing, you probably got to like 20 mil, depending on how powerful it is. And you can do like things like styrofoam, so you can do prototyping and that type of thing. Then you got CNC milling. So same sort of thing is that you'll have your file and you'll send it, and it will send it coordinates. I know I was right the first time when I said X, Y, and Z. So it works in the same sort of way, is that basically your work will be clamped into the machine, like bench there, and then what will happen is the cutter itself doesn't move. Okay, what happens is the bed, much like the normal mill, is that you will have, my mouse keeps disappearing, the cutter stays still but just spins. And then the bed that's holding the piece is the thing that actually moves. So Z up and down, Y forwards and backwards, and X left to right. You can, obviously, if you're doing like, not cheap, but if you've got a less modern machine, a less high-end machine, each time you have different styles of cuts you need to do, you'd have to stop the machine, change the cutter, and do it on there. But if you've got really modern ones, really high-end ones, what you can do is have one and they'll have like multiple heads. So when it needs to do a different cut with a different cutter, it will change itself out depending on what the job is. You also need to have things like lubricant on there to stop it from hardening, because if you're doing typically it'd be metal, it will get red hot, so you'll have to have coolant spraying on it to stop the metal from deforming. And nowadays they are also going to be enclosed, basically to stop any like health and safety risks that might happen. You've then got CNC turning. Again, works in the same sort of way, but much basically like a center lathe. So you'll have your part into the lathe, so you take like aluminium bar or something like that, and you're going to have a cutter, and essentially it will figure out how deep it needs to cut and whereabouts and along. Same sort of thing, obviously, but all you're going to do though is it's going to be X and Y. You're not going to do Z on a lathe, because you need to make sure the cutter is central to the middle of the material, but you're still going to move side to side and forwards and backwards for depending on what you're doing. Really good at doing complex things like cutting threads or boring certain parts out. Okay, Blotter Cutter. So Blotter Cutter is one, again, I would assume quite a few people probably aware of. We've got one upstairs in the workshop. So this will convert 2D CAD drawings into, again, coordinates X and Y axis. And what you'll do is, so we will use 2D design, and this will typically use to cut things like vinyl or card to do like graphics and that sort of thing. Essentially what you'll have is you'll have a little blade. So again, my cursor keeps disappearing. On this little part here, you've got a blade that's going to move left to right. So all it's going to do is X, and it's the material that moves forwards and backwards. So the blade is just going left to right, and applying pressure to cut things out, and the material is going to be fed in and out by rollers. Then you've got virtual modeling, and this screenshot is a very, very old virtual modeling, clearly. So again, we do this sort of thing in Fusion, where you can basically let you create and model things out virtually before you do things for real. So if you're, say, in industry and you're doing like architecture, or you're putting out new layout for like a workshop, rather than moving things around and then deciding, oh no, I want it to be over there now, and the thing weighs a ton and you've got to get 6 guys and loads of machinery to move it. You can map out the whole layout before doing it, and it makes your process a lot easier. Okay, these are more of the A-level side ones. So we'll start with finite element analysis, FEA. So this is basically a simulation that you can run within a CAD package that will let you test, run a simulation to test the strength of things. So say if you take like a bridge, we've got the example here, is if it's blue, it's fine, no stresses. And obviously the darker the colour goes, the more stress it is on there. So what it will let you do is test things like vibration, shock load, and you can see if things are going to hold. So you've got a simulation, say you're going to have X amount of weight, so a lorry, and that's going to be like 16 tons. And you're like, okay, how can that hold it? Now you do that with things like bridges, you can do that with architect like buildings, so you can actually physically tell before, because obviously you can't just build it and then, is it going to last? No, I hope so. And then someone comes along and it collapses, because that's not okay. So you need to do these tests beforehand. Rapid prototyping. This typically nowadays actually is mainly used to refer to things like 3D printing, which actually isn't that rapid depending on what you're making. I mean, you can do complex parts, but I've printed things before that take like 16 hours to print. But the idea being that you've got your CAD design, say it's an STL, put it into your Ender or your Ultimaker, whatever it is, and then make a complex model. Excuse me. You can also do it with things like with the routing, where you might have like styrofoams in your router and it'll cut out of that way as well. So there's a few different ways of doing it, but rapid prototyping typically refers to like 3D printing nowadays. Then you got computational fluid dynamics, and look, I can actually get F1 into a YouTube like a theory video without forcing it. So CFD again is a simulation that will let you simulate how fluids or air or gas will flow past an object. So we'll take F1 as an example because actually aerodynamics matter massively. It'll let you simulate and see where like the drag and where how much is being weighted and how well it's like moving through and how fast are you expecting it to be. Because obviously if you take like F1 and they're flying all over the world to race and they're trying to get like 0.2 of a second faster, which to words sounds like nothing, but in racing 0.2 is actually quite a lot. You can't just randomly make things and hope for the best. You have to test them first, check it's going to work, and then try it. Because if you just make things randomly and hope it works, if it doesn't, you waste loads of money. So you need to slowly test it. Okay, right, let's make it. Okay, let's put it on. Fuel deposition modeling, which is basically FDM 3D printing. So there are two kinds of 3D printing. One is resin and one is FDM. So we're not going to go over resin printing really, because it's not as complex as FDM. So this is the idea that you like basically how 3D printing will work. So what will happen is once you've got your 3D model, you'll export it as what's known as an STL file. It then needs to be sliced in a slicer. So we typically use something called Cura, which is just a piece of software. And essentially what that does is that literally slices your material into loads and loads and loads of layers. Because what will happen if you've never seen a 3D printer work is, say you've got the bed here down at the bottom. I want to print on here. You have your filament, your roll of filament. So we typically use PLA. Is it'll be fed in there, it will heat up, and then what's going to happen is that material will heat up and be fed through the nozzle, and it will stick to the bed. And layer by layer, it will slowly build up. Now you can get some 3D printers that have multiple different heads, so you can do loads of different colors at the same time. You can get 3D printers that can print in things like metals. So there's loads of 3D printing actually is such a thing that gets developed so quickly. There's so many people looking at making these things. You may have seen, particularly in like the States, where they're 3D printing like exterior like houses and those sorts of things. Electronic point of sale. So this, before I go through this, I bet most of you thought that a barcode is what sets a security alarm off in Tesco's if you walk out without paying. That's not actually true. What the barcode is doing is when they scan it, so when you like got the till and the beep beep, so that barcode is doing a very specific job. What's actually happening is a light is shining and then bouncing off the barcode back to the machine, and what that is doing is telling the machine what the object is that you bought. So yeah, apart from the fact that it tells you the cost, it also controls the stock level. So say you bought baked beans, what it'll say is, okay, that's baked beans and that is 89p. But what it'll also do is tell the system, okay, someone just bought 6 tins of baked beans. I don't know why you're buying 6 tins, but you're hungry. What it will do is on the system, it'll go, okay, we had 500, someone just bought 6. And then, okay, someone else has just bought 14. And then someone else has just bought 50. And once it gets down to a certain level, they will automatically reorder more. So you basically keeping track of stock rather than having to count by hand and by person 1, 2, 3. Automatically, it's letting you know, okay, you're dangerously low on baked beans. You've got 50 cans left. You've got to order some more. It'll also let you use the information like marketing. So that's why when you use like your club card at Lidl or Tesco's, because you've scanned in your thing, they're, oh, well, you bought a lot of baked beans last week, so do you want an offer on baked beans this week? And you're like, oh, yes, I do. So that's what the information is also used for. And the last thing we're going to go through, I'm pretty sure it's the last, is production planning and control networking. So this is basically how you're trying to automate processes to make it as efficient as possible, basically. Okay, So there's a few things like, so if you've done business with us before, you probably heard the term just in time. So just in time is the idea behind what you don't want to do is pay for storage, buy all your materials beforehand, store it, make loads of products, and store them in another factory because you've got to pay for two factories, one to store the materials, one to make for the actual product. And then if no one buys it, you're kind of stuck with it. And there's loads, I mean, there's more issues to it than just that, but that's not the basics of it. So just in time, we'll think, okay, one person just ordered this product quick. Okay, so what we'll do, automatically, they'll start ordering in parts. Okay, so we need this material from this shop and we need these parts from this shop. And automatically, because that order's been placed, those parts will then get ordered as well so they can get delivered at the same time for when you need it. So you're not wasting time, or you're not wasting resources, sorry, paying to store excess material and excess produce. So what you also have is like a master production schedule, sorry. So that lets you plan out how many will be produced in a particular time period, and then what else is going on at that time as well. So you're only going to make as much as you need to make rather than storing it somewhere else. So you also have a Kanban system to make sure materials arrive at the correct point in production. So you'll basically have software that knows, okay, at workstation 2, we're going to need 60 bolts because this part is coming. Or we're going to need a lathe, we're going to need the cutters at this time. So what we'll do is basically an all automated system that knows the whole process and knows, okay, at station number 2, we need these parts. At station number 3, we're going to need these parts. So there's the whole idea of keeping it automated to make sure parts are there when a worker needs them. Because as a business owner, what you don't want to do is be paying workers that aren't doing anything because they're waiting for systems or they got to walk over there and go and get the parts and come back. And it's just sort of seen as like wasted time. Okay, last thing, there are 8 questions on the screen. Can you pause the video, have a go answering the 8 questions, and then I'll put the answers on the board. Okay, answers are on the screen. Hopefully you found that useful. If you've got any questions, let me know and I will get back to you.